let's see here. Relatively finished things.
I don't think this is acceptable.
All right, let me. Oh my goodness. I'm sorry, guys. I got carried away trying to wait for a certain person. But anyway, he knows who he is. What's that?
I can't stay really past 5 very much today.
Ah! But you should have told me this before I delayed. Ay, ay, ay.
I forgot.
I'll talk faster. So this is Psalm 24, verse 1. It says the following. The earth is the Lord's and all it contains, the world and those who dwell in it. So you notice that this includes everybody. It's like whether you believe in God or not, you're still the Lord's. Sorry to tell you, atheists in the audience. I don't think you guys, but so I'm trying to make my videos more annoying. So I feel like I'm sort of, oh look, what in the world? Great, googly moogly. I will begin with a word of prayer. Dear Father, we thank you for this day and for this class. Just help us to use this time wisely, Lord, to glorify what we do, Lord. In your name I pray, Lord Jesus, amen. Well, all right, so we are in so today I want to talk to you guys about manifolds with boundary and hopefully tangent space. And also just a collection of, things in between that. I'm focused here for the most part. These are, basically we're looking today. Today I'm in John Lee's book. Select wisdom from chapters. Well, I guess it's, goodness gracious, I don't know, maybe 2 and 3, maybe something in 1 here even. So let's just get to it. In fact, yes, the first thing is from chapter 1. So I read chapter 3 in Jeffrey Lee's book, and it's wonderful, but it just doesn't quite suit my purpose here today. More about that later. So let's talk about what's a manifold with boundary. So to start with, we have to talk about so-called half spaces. All right, so closed n-dimensional half space, and I think it's actually upper half space. Upper half space is Hn, which is equal to x1 xn, such that, of course this is in Rn, my bad, in Rn, such that xn is greater than or equal to 0. All right. And he says we'll use the notations interior and to denote the interior, and boundary of Hn to denote the boundary. So like in particular, int of Hn is, let me just get to the point here, x in Rn, there we go, such that xn is greater than 0, and the boundary of the upper half space is x in Rn such that xn is equal to 0. All right. Closed n-dimensional upper half space. All right. And so these are the model spaces that John Lee's book uses to describe manifolds with boundary. If you read Jeffrey Lee's book, he takes a far more complicated perspective, which is probably nice for examples. And his typical model space is much more nuanced. It allows for essentially arbitrary upper half planes defined by some sort of hyperplane in Rn. So like if you want a more sort of, cluttered is the wrong word, but a less easy version of this, look at Jeffrey Lee's book. All right, but this is nice because then in this book, if you're asked to prove something about manifolds with boundary, well then this is your definition. You'd rather not prove them in Jeffrey Lee's definition. All right, so nicer bookkeeping here. And also, there is like a theorem that any half space is like isomorphic to this half. Any closed half space is isomorphic to this one. So like just to draw a picture, if I was to talk about like this space, right? You know, above the line, say y equals to, I don't know, x plus 1, right? This guy up here, these points up here. That is the same, right, as a space, as just the closed, you know, just plain old H2. You could prove that. Those theorems are given in Jeffrey Lee's book. Okay? All right. So, n-dimensional topological manifold with boundary, he says, is a second countable Hausdorff space in which every point has a neighborhood homeomorphic either to an open subset of Rn or a relatively open subset of Hn. All right? So, what is a relatively open, what's a relatively open subset? What's that even mean? Relatively open subset of Hn. Let me draw you a picture. So what we're talking about here, right? So here's my Hn. I'll draw it like it's H2. But a relatively open subset of Hn is one which is formed by the intersection of an open set in Rn with Hn. So it's either just, you know, it could be something like this up here. It could be a U like that. That'd be fine. You could do that, right? But the other thing you could have would be something like this down here. And in that case, the intersection of U2 with Hn would just be this piece right here. So that little half disk kind of thing, that would be relatively open. So relatively open subsets of a closed set, or a set with an edge, they're formed by the intersection of the open sets in the larger space with the smaller space. This is called the relative topology, right? You'll learn about it in a couple of weeks there. But, anyway, so anyway, getting to the point here, if we have phi, a mapping from U to Rn, all right, where either phi of U is, you know, open in Rn, or phi of U is open in Hn, all right? So it could be either one. Then that's a chart on a manifold with boundary, okay? And what would you guys think it would mean? So if I say open in Hn and let's suppose we say, in addition, let's add on, you know, like phi of U intersects the boundary of Hn non-trivially, all right? Then that would be what kind of chart? That would be called this right here would be an example of what's called a boundary chart. So a boundary chart is one which, you know, hits some of the boundary of Hn, all right? And otherwise it would be called an interior chart. What's an interior point? What's a boundary point? I think you guys can make sense of those terms. I won't define them. It is kind of what it sounds like. An interior point is a point inside an interior chart. A boundary point would be a point that maps to the boundary of a boundary chart. All right, so let me tell you guys a proposition. And so proposition, this is 1.38. It says the following, let M be topological n manifold with boundary. All right. And number one, the interior of M is a blank. That's part A, actually. Part B, the boundary of M is closed, in the topological sense, subset of M. All right. And is a blank. And let's see here, C. If M is topological manifold, if and only if the boundary of M is empty. And you know who I learned that from? Let's see here, D. If n is equal to 0, then the boundary of M is empty, and M is 0 manifold. So guys, let's just talk about this proposition. I think if we understand this proposition, we've got a pretty good entry-level understanding for what a manifold is with boundary. To start with, John Lee just looks at the topological aspect of it. Next, we'll talk about the smooth structures. All right, there's still more to talk about in terms of defining it as a smooth manifold with boundary. So what do you guys think? What should the interior of M be? If M is a topological n manifold with boundary, the interior of M, right? It's what? It's open. True. That's true. But what is it? It's just an n manifold. All right. And by that I mean it is homeomorphic to Rn. It's locally homeomorphic to Rn everywhere. It is not true for a manifold with non-trivial boundary, right? If there actually is, if the boundary is not empty, then that means there are points in the manifold which are not homeomorphic to Rn, the points on the edge. So that's the answer here. Partial M is a close. I think I've lost some. I'm sorry, guys. Oh, and I should have said, and without boundary. I knew I forgot something here. Without boundary. So the interior has no boundary. Its boundary is empty. The boundary of M is a closed subset of M, and it is actually a n-1 dimensional topological manifold. All right. And I think you could say without boundary, but he does say without boundary. The boundary of the boundary is nothing. So if I was to say like the boundary of M, the answer is it's empty. Okay. And let's see here, what else? M is a topological manifold if and only if the boundary of M is empty. The reason for that, again, is if there exists a boundary chart, that means there's points in the manifold which are not homeomorphic, locally homeomorphic to Rn, which is not allowed, because that's essentially the definition of a topological manifold, is that there's a local homeomorphism with Rn at each point, right? Okay, so that's that. So how about smooth structures on a manifold with boundary? How's that go? Let's talk about that. So essentially this begs the question of how do you decide that, yes?
So just clarification here, a manifold with boundary is not a topological manifold.
A manifold with boundary is not a topological manifold unless it has trivial boundary.
Meaning empty?
If the boundary is empty, then it's a topological manifold. So topological manifolds are a special kind of manifold with boundary. Yeah. But generally, no. Yeah.
Does that make the boundary a topological manifold?
Yeah, the boundary of a manifold with boundary is itself a topological manifold. Yes, very good. Yep.
I guess if we take out.
Oh, you want an example? Let's get.
Never mind.
So yeah, let's.
Boundaries of n minus one dimensional.
Don't make me give you the formulas, but if you'll allow me just to claim some things by, you know, kind of like principles of. Oh, that makes sense. So example 1, we could let like M be the ball of radius n. That's a subset of our. Well, oh man, I'm not sure about his notation. Give me a second.
Should not be n plus 1.
Well, that's my question. No. So this is Rn, actually. And that was, yes. I know why you want to say n plus 1, because you're thinking, so this is the closed ball, right? So specifically, this guy is equal to what? It's equal to x in Rn such that the length of x squared is equal to 1, right? That's not true. That would be the n minus 1 sphere, right? So to make it the ball, I have to do less than or equal to 1, right? So I have not proved this, but it is true that the boundary of M is going to be the n minus 1 sphere, right? Which is going to be, you know, x in Rn such that the length of x is 1. And the interior of this is the open ball. And maybe I have forgotten his notation. I wonder if I have to have a ball. I wonder if this is the open ball notation. Let me be careful, guys. Let me be careful. He does have, yeah, that's the open ball. If I want this to be the closed ball, I must take the closure. Easy enough. That's right. Did you guys already do that in topology?
And complex analysis.
Oh, right.
You introduced it like once, and you're like, oh, that's confusing because it's z bar.
Yeah, it's annoying, but this is the thing. The closure is well-defined. You can define the closure on an arbitrary topological space. It's a general topological notion. Anyway, so the closed n ball, the boundary of which is the n minus 1 sphere, the interior of which is the open n ball, which is just Bn. So like int m here would just be that guy. And so you can start to appreciate why the boundary of the boundary is empty, right? What's the boundary of an n minus 1 sphere? What's the boundary of a circle, right? A circle is the boundary of a disk, right? The two ball, the closed two ball. And the boundary of a circle is nothing, right? Okay, so this is probably the quintessential non-trivial example. It's not just closed half space itself. Jeff really says to think of a manifold with boundary, you should really have those two examples in mind. The closed half space and the closed ball. Those are the two, base examples of these things. Okay, so what do we mean? So to define a smooth manifold, we had to define what it means for, we had to define the smoothness was captured in terms of transition functions, right? And so let me just read what he says here on page 28. He says, let M be a topological manifold with boundary, as in the manifold case. This is on page 28 of John Lee's book. And he'll let M be a manifold with boundary, as in the manifold case. A smooth structure for M is defined to be a maximal smooth atlas, a collection of charts whose domains cover M, and whose transition functions and their inverses are smooth in the sense just described. With this such a structure, M is called a smooth manifold with boundary. Every smooth manifold is automatically a smooth manifold with boundary, it's just that the boundary is empty. All right, so the question is, what's that smoothness? Well, let me show you the example that he gives on page 28. So let me just sort of give you the basic idea. If you have F, and it's a mapping from, let's say, C, which is some closed subset of, I don't know, Rn, all right, to Rm, then this is smooth if there exists F tilde, which is a mapping from, like, let's say, U tilde subset of Rn to Rm, where U tilde is open, containing the closed set C. This is essentially the idea we saw in complex in different places, where we had to assume, like, our whatever object we were looking at was defined a little bit beyond the curve on some sort of open set, so that we, had rights and privileges to do things on that slightly larger set, and then restrict to the closed curve to make things nice. Same kind of idea here. And let's bring it to life. This example in John Lee's book I found to be helpful, because you read this stuff and it just kind of leaves you like, what does that even mean? Could you give me an example? Well, yeah, actually I can. Here it is. So, example 2. We have B2 is a subset of R2, the open disk, right? And he says let U be B2 intersect H2. Ooh, check that out. What's that? So let me recreate the magic here. Here's his picture. So, and all right, so this guy, right? This is U right here. It's the intersection of the upper half plane, right, with it's the intersection of the upper half plane with the closed upper half space, all right? So what we call this in plain language would be what? It's the what? I want to say it's not a hemisphere. What's a half? It's a half disk, I guess. It's a taco. I'll allow it. So cool. It's a half of a disk. Yeah, it's not a closed half disk either. It's kind of funky, right? Like it's got an open upper edge, but then it's got a closed lower edge. However, this is a open set in the relative topology of H2, because it's the intersection of, yeah. Anyway, so the question is, if you've got a mapping from this guy over here to, Euclidean space, what does it take for that to be smooth, right? Well, okay, so if we're talking about a point like up here, well, there's really nothing much to say. A point up there, we already defined how to talk about smooth up there, right? But technically speaking, if F is a mapping from, F is a mapping here from U to there, and if we got X here on the boundary, it's a little bit outside our scope. We don't have a definition yet for that, all right? So what he says is you just imagine, like this, U tilde, a little bit bigger, right? And let me see here. Now he actually has a formula. His formula doesn't match his picture. That's kind of funny. All right, anyway, so here it is. F from U to R. So the picture is more general than the example here, paragraph. That's fine. F of xy is the square root of 1 minus x squared minus y squared. All right. He says F extends smoothly to all of B2. Therefore, f is a smooth function on U. Do you guys see that? So we can just as well extend to, let's say f tilde, a mapping on, U tilde, which is a subset of B2. B2 to R. By the same formula, it's smooth. Why? Does that make sense? Where is this formula not smooth? It's not smooth when the distance from the origin is 1. But by definition, this is the open unit ball, so we don't quite get there. So it's fine. So this would be an example of a smooth function on this. Well, it's a manifold with boundary that just also happens to be a subset of, R2. So this is how we have to judge the smoothness of a mapping on a manifold with boundary if we've got like an edge point. The question is, can we extend a little bit, and is that extension smooth in the sense we talked about before? Meaning that it has a Jacobian, which has, derivatives that are themselves continuous of all orders. Yeah.
In the definition up there, it's smooth if there exists df with tilde. Is tilde supposed to be smooth as well?
Oh yeah. Smooth. Thank you. Yeah, that's kind of the point. I should probably write that down. Yeah, thank you. I hope I at least said it. Yeah. Okay, so it's also helpful to have an example of one that's not smooth, and John Lee, to his credit, gives us both. So let's look at the other one here. So the other, g of xy equal to the square root of y. He says this is continuous on U. All right? But, and smooth, he says it's even smooth on what? On U intersect the interior of H2, right? In other words, this guy, it plays nice as long as we're like somewhere up in here, right? But it has no smooth extension to any neighborhood of the origin, right? So if you try to take this function, if you look at the origin, right? And you pick any open neighborhood, right? Doesn't matter how small you make it, there exists, like it's impossible to have a neighborhood of the origin where this is not smooth, because this has a vertical tangent at 0. 0 is in every open neighborhood of the origin. So it's impossible to find a smooth extension of this guy. This is not a smooth function on U. Now, of course, that's kind of obnoxious, right? Logically speaking, to prove something's not smooth, you need to show that there does not exist any open neighborhood of some point such that the extension is smooth. But anyway, that's what it is. All right, so then he goes on to explain, like, smooth coordinate half balls, regular coordinate half ball, a bunch of just sort of modifications of the language for manifolds with boundary. You guys can read that. Don't have much to say about that. I wanted to go through this example because that's kind of like the heart of the matter. Oh, and this is also important because I saw this pop up in a later proposition and it like mystified me. I was like, wait a minute, what's going on? It was so weird. There's a theorem later about a product manifold, and it, for some reason, only let there be one of the products having a boundary, but not two. And so this is an important comment on the top of page 29. One important result about smooth manifolds that does not extend directly to smooth manifolds with boundary is the construction of smooth structures on finite products. So in particular, so this is just caution. even if we think about the most basic thing, open end space, Cartesian product, open end space. That's actually not the most basic thing. I suppose the most basic silly thing to do would be like, you know, probably this, right? H1, Cartesian product H1, which would be what? 0 to infinity, Cartesian product with 0 to infinity. I can actually draw a picture of that. That's this space, right? That space, H1 cross H1, certainly not a manifold because it's got a boundary. It's got boundary points which are not they're not homeomorphic to R2, right? And it's not a manifold with boundary either because while these points are fine, right? This guy right here is not, there is no homeomorphism from that space, from like a neighborhood of that point to a closed upper half space. It will be homeomorphic to something that's got a corner in it. So when you take the Cartesian product of like two manifolds with boundary, you can end up with a corner point. So what would your next question be? Yeah?
Well, I was going to ask if there was anything we could do with conformal mapping, but I guess probably not if you're crazy.
Conformal mapping. I suppose you could, but that would be like, yeah, I don't know. I'd have to think about that. But the answer is you can work the homework problem in John Lee's book where he develops the notion of a manifold with corner. So if you can do manifolds with boundary, you can do manifolds with corner. And so there is a way of treating this systematically, which is nice because, of course, there are examples in Calculus 3 where we have things with corners, right? So you can develop a theory of manifolds with corners, but that's not something we're going to do in class. There's like a homework exercise about it. Maybe we'll have to say more about it when we get to like the generalized Stokes theorem in here later, all right? So that's just a warning. So that is why when you look at theorems later, sometimes if it's a theorem about a Cartesian product of a bunch of manifolds, they will insist that there's only at most one of them as a manifold with boundary, because if there's two of them, you get corner points, which is not something that's a feature of a manifold with boundary. All right, so there's theorems like the, and this theorem is kind of the same issue. Let me just tell you. So if M is a smooth manifold with boundary, this is theorem 1.46 in John Lee, manifold with boundary. And P is an element of M. If there exists a smooth chart U comma phi for M such that phi of U is a subset of the upper half end space, closed upper half space, and more than that, phi of P is an element of the boundary of the upper end space, then check this out. The same is true for all charts which contain P. All right. In other words, the boundary is a genuine geometric feature of the manifold. It's not something that's just some sort of like coordinate effect of the chart or something. Like no matter what chart you pick, is going to be the case that the the boundary point, if you have a point on the manifold which maps to a boundary point in your chart, that has to happen for every single other possible chart you can pick at the point. Right? The proof appears to be by contradiction, and it's about half a page long. I'm going to skip it. So, but it's on page 29 if you want to read. There's a number of such theorems. You'll find slightly different ones in Jeffrey Lee's book if you read. But basically, they all speak to the fact that the boundary of the manifold is sort of like preserved. To use more colloquial language, it's a thing. All right. All right, at this point, I wanted to I'm going to skip ahead to chapter 2. And in chapter 2, John Lee had a lovely list of smooth maps, which I thought would be good for us to just enumerate and appreciate together this list of mappings which are smooth, because it will be comforting to us later if one of these comes up in like a larger context to already know, oh, that's a smooth map. We know that's smooth. We talked about that before. He wrote it on the board. That means we don't have to prove it, right? I guess unless I assign you the problem which says prove it. But yeah. Oh. I guess you could always rebel and just not do it. I mean, but that would be silly. It is your class after all. I mean, it would be an insane thing to ask for some professor to, like, take time to plan a class and then just not even show up or do the work for it. And then after that, to think it was okay, it was safe somehow to ask that same professor for a letter of recommendation. It's a funny thing. It's an interesting phenomena. Oh no, that stays. I wonder what it means. Oh well. So some examples of smooth maps.
That you laughed at when he asked.
Whoever are you talking about? Let's see here. So some smooth maps. We could anyway. All right, I'll shut up. Smooth maps. So here's his litany of examples. So this is page 37 to 38 in John Lee's book. Any map from a zero-dimensional manifold into a smooth manifold with or without boundary is automatically smooth because each coordinate representative is constant. Any map from, let's say, I'll call it Z to M, it's automatically smooth. So this is, let's let M is going to be a smooth manifold. Smooth manifold with or without, boundary. And here, this Z I'm saying is a discrete space. It's a zero-dimensional manifold. What's a zero-dimensional manifold anyway? Yeah, I mean, it's not just zero. It could be a collection of points. It's basically a collection of isolated points.
Discrete.
It's a discrete space, is another way you could say it. What is this? Well, this is like whoever cares about this. Well, what does this mean? This means that any sequence, any manifold valued sequence is automatically smooth. Why? Because you can't really test how the function varies at the points, right? Because there's no other points in the domain. There's just 1, 2, 3. So by default of the definition, that's automatically smooth. In a similar sense, in real analysis, if you really paid attention to it, a sequence is a continuous function. It has to be. Anyway, you start thinking more about that, you'll realize it's really important that that is the case. Part B, if we have a circle S1, I don't know if I can draw that. I want to learn how to draw that. How do you draw that? I've got like a double S. My double S's never work out well. Anyway, S1. Given its standard smooth structure, you can talk about the mapping epsilon from the reals to, I'm going to go back to my usual S1, defined by epsilon of t equals e to the 2 pi I t is smooth. Why is it smooth? Because, all right, let's draw a picture here. Here's your S1, right? And here's R. And so, you know, there's epsilon, right? And then what's the, what's the usual I mean, whatever you want. Let's see here. Suppose this is the angle function I'm talking about, like this one. So there, this is theta. I've illustrated the theta equals to, I guess for us, oh man, oh my bad. Let me be lazier. Here's the usual in complex analysis, arg. Right, the principal argument, it gives you back an angle between minus pi and pi not included, right? And so like, what's that?
Not this again.
Not this again? Oh yeah. Don't worry, it's harmless enough. Well, I guess it's the same harm as before, 2 pi I t. So the theta does what? The coordinate chart theta on the circle, it just picks off the standard angle, right? And so if this is t and we're mapping it up to here, then down here is the other copy of r, and I think he calls this thing epsilon hat for like the local coordinate representative of it. What's the formula though? Like epsilon hat of t, it's just equal to, well, t plus some constant, where the constant is determined according to how t fits, whether t is inside the, it's whatever you need to add to t in order to make it fit into minus pi to pi. But that's just a constant for a given t, right? And so that's manifestly smooth. Therefore, this is a smooth chart, smooth mapping, because it has a local coordinate representative, which is smooth. Okay. I won't go into that much detail in every one of them, but I thought it was, I think it's helpful for us to like take a second to like unpack what we're saying. All right, so let's do that on occasion here. See, epsilon n, as he calls it, a mapping from Rn to Tn, the n torus, given as follows by epsilon n x1, x2, xn is equal to, guess what? E to the 2 pi I x1, yada yada yada, e to the 2 pi I xn, right? This is smooth by proposition 2.12. What was that? He says this is smooth by proposition 2.12. So proposition 2.12, all right, it says the following. It says, suppose that M1 through MK and N are smooth manifolds with or without boundary. Oh, this is the one. This is the one I was talking about. Let me write it up here. Proposition 2.12, it says, you've got M1, M2, MK, and N, smooth manifolds with or without boundary. All right, such that at most one, M sub I has boundary, right? And if, let's say, pi I, a mapping from M1 cross cross MK to M sub I, denotes the projection onto the MI factor, all right? In other words, pi I of, P1 PK is just equal to what? It's equal to PI, right? So the ith projection. Then if you've got a manifold map F that goes from the smooth manifold with or without boundary N to the product manifold M1 cross cross MK, all right? Well, this is smooth. Where? What? If and only if what? Each component function, which would be nothing more than pi I composed with F, which would be a mapping from N to MI, is smooth. So what this little proposition says is that if you've got a mapping from a Cartesian product of smooth manifolds, if you've got a mapping who takes its values in a Cartesian product of smooth manifolds, then smoothness of that map can be judged by the smoothness of each component map that forms the map. And that's why this proposition is relevant to this example, part C, you see, because each component map here is precisely the previous thing, which we've already proved is smooth, right? Is that an exercise? Oh, come on. Oh, wait a minute. Proof, problem 2.2. I should probably assign problem 2.2. Problem 2.2 is the proof of this thing, which should probably be healthy for you guys to do. Let me move on here. D. If we have the N sphere Sn with its standard smooth structure, the inclusion map. So this symbol frustrated me as an undergraduate. I've only slightly mellowed to it, but it's not I, and it's Yoda, all right? N+1. So this is the inclusion map of Sn into Rn+1. He says it's continuous because it's the inclusion map into a topological subspace, and it's a smooth map because its coordinate representative with respect to any of the graph coordinates is, all right, so what is its coordinate representative? So he puts a hat on the coordinate representative, and he points out that the formula for it is equal to, here's how it goes. We've got iota, composed with phi plus or minus. These are the ones I haven't actually explicitly made formulas for yet. Like I didn't get to this in my video, I've alluded to these things, but I think this is this formula here kind of more or less shows you what they are. So that is just equal to u1 ui minus 1 plus or minus the square root of 1 minus the length of u as a vector squared, of course. And then you got yourself a ui and un. That is the local coordinate representative of the inclusion map of Sn into Rn+1. I could draw a similar picture to the one I already drew up there if it was helpful. I don't necessarily think we need to. Now, my question to you would be, where would this map get into trouble? Or another way to ask this is, why is this smooth? What would the trouble be? Notice that, the length of u squared is hold on a second. What? I'm getting too far away from what these charts were, right? These are the north-south, east-west charts, but except for the n-sphere, and the context, remember, is to exclude poles.
Yep.
So these are exactly, it's the subset of Sn such that such that this is less than 1, right? The thing that's tricky about it is the set Sn is the sum of like x1 plus x2, x1 squared plus x2 squared plus da 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 plus xn plus 1 squared equal to 1, right? But here, this is just an n vector in U. So we chose the chart, the domain of these things is explicitly constructed such that, you know, we don't get to U, we don't get to the coordinates that have zeros in everything and then plus or minus 1 in the other. You know, so you never actually reach the length of U being 1 when we put in context here. Therefore, it's smooth. And then his example E is from Rn plus 1 without 0 to real projective space. And he points out that this is a smooth map, and he writes down the local coordinate representative for the projection from so here we've got pi from Rn plus 1, take out the 0, and we're mapping to Rpn. What's the notation for that usually? You guys remember? Pi of x equals to what? What's the nice notation for this? Yeah, just what's that? Allowed to cheat? Well, yeah, you can look. It's fine. It's just bracket of x, right? So this is equal to specifically like tx such that, you know, t is in reals, right? It is the line through the origin in the direction vector x, right? That's a typical element of the real projective space, which is a line, right, through the origin. And well, he says that the local coordinate representative for this thing, right, the local coordinate representative for this guy, he claims is as follows: pi hat of x1 through xn plus 1 is equal to, now that's a little, oh, I'm dumb. That's fine. Let me draw a picture here. So here you've got Rn plus 1 without 0 right up here. And then, of course, you got the identity down here to Rn plus 1, right? Over here, we've got pi, Rpn, right? And then we've got the coordinate chart, whatever I guess he uses phi for those, right? And down here, it's n-dimensional, right? And okay, so like the local coordinate, so that down to this is the pi hat he speaks of, right? And so pi hat is going to be phi composed with pi, you know, fed this x1 through xn plus 1, which when we sort through the definitions that we have looked at is phi of, you know, the line with homogeneous coordinates x1 through xn plus 1, which by definition was x1 over xi, and then dot, 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 xi minus 1 over xi. And then we skip the ith one, we go on to I plus 1. And so forth and so on until we finally get to the xn plus 1 over here, xi. All right. So that is the formula that pi hat has, taking a point, here, x maps to this thing. Let me call this thing y. Maps over here to y. Right? Is that smooth? Is that a smooth local coordinate representative? Well, what would be troublesome here is if we actually had xi equal to 0, right? But we don't because of the context. Remember, the domain for this chart assumes that we're looking at lines whose direction vector has non-zero ith coordinate. Therefore, these divisions are harmless, and this is a smooth map. Therefore, the projection map is smooth with respect to the standard smooth structures on our n+1 and real projective space. His next example doubles down on this further. He defines a mapping Q from Sn to real projective space as just restricting restriction of pi from the previous example to Sn, which of course is a subset of our n+1, right? But what does that make Q? That makes Q equal to the composition of pi and iota. I just really, really want to write a dot on that. Like, I can't tell you how much I want to just put a dot. Like, it's just, anyway. Now that's a smooth map because it's the composition of smooth maps. And something I probably should make you guys prove is that the composite of smooth maps is smooth. Oh, you did? Oh, good. Oh, good, good, good. Yay. I guess I haven't done all my homework yet. And then finally, he has, if you have M1 through MK smooth manifolds, all right, then if you look at the ith projection map from the Cartesian product of these guys, right? He says, well, that's smooth because it's coordinate representative to any of the product charts where we define the product chart on the Cartesian product of K-smooth manifolds. It's exactly just the coordinate projection. In other words, it's pretty obvious that this is smooth if you just look at the coordinate representative. All right, so moving on here. Excuse me. There is a beautiful, so we talked about, we defined diffeomorphism before. You guys have actually proved some things are diffeomorphisms. But there's some examples of diffeomorphisms in the notes which are worth us writing on the board and appreciating together. So this is example 2.14 in John Lee. And here he gives us mappings. F is a mapping from the open n ball to Rn. And G is a mapping from Rn to the open n ball. All right? And here's the formulas. F of x equals to x over the square root of 1 minus the length of